Hi, hello everybody. Welcome back. And today we are going to discuss about ligand field theory. Hmm? So we started off with the discussions on valence bond theory, wherein we said that it is all regarding the hybridization of the orbitals, right? And then after VBT, we moved to CFT, wherein they said that there is no concept of hybridization or covalent bond formation. Instead, what you have over here is just based on ionic interactions. This is what CFT said. Now, what we're going to learn is about ligand field theory, LFT, or it is also called adjusted CFT. It is also called adjusted CFT, wherein they take into consideration both the ionic part, which was explained in CFT, as well as the covalent part, which was explained in VBT. So it's a mixture of both ionic as well as covalent characters, which are being described over here. Adjusted CFT. Okay, now why did we need another theory when we had CFT, which was explaining quite a lot of things? Okay, so the problem was in CFT only, so the particular problem was only d orbitals were considered, right? We started off with the splitting of d orbitals, whatever the geometry may be. It might be octahedral, tetrahedral, square planar. Then we discussed a list of geometries, square pyramidal, trigonal bipyramidal, so on and so forth, wherein only d orbitals were considered for interaction. But what we can see in LFT is in LFT, we do consider the s orbitals. Okay, we consider the p orbitals and d orbitals. So all these orbitals are considered in adjusted CFT or in LFT. All of these are considered. Okay, so based on the representation, now you know that s is just one orbital. If you take p, there are three orbitals, right? Which are they? Px, py, and pz. And if you take d, there are five orbitals: dxy, dxz, dyz. These are the non-axial ones. And we have axial dx square, y squared, and dz squared. These many. Okay, so SPD. So in total, how many orbitals are there? 9 orbitals. So in LFT, we do consider all of these 9 orbitals. And based on the symmetries, they are classified. Now, what do you mean by symmetry? Again, let me try to explain. Let's say you have S, P, and D. Already we know that in octahedral geometry, the d orbitals are represented as T2G plus EG. Am I right? T2G plus EG. So this is based on the symmetry, their degeneracy, etc. T2G and EG. Similarly, if you take the octahedral geometry, now what we are going to discuss is about the MO diagram. You can note down the heading. MO diagram in octahedral system. Octahedral system. Okay, so if you have an octahedral system, the symmetries of these orbitals are for D, T2G, EG, you're familiar. For P, you have PX, PY, and PZ. So the degeneracy is 3. Corresponding to 3, always your alphabetical notation that you'll be using will be T. Okay, and it is T1U. It is T1U. And for S, it is non-degenerate, A1G. So these are the 9 orbitals and the corresponding representations. S, P, and D. S corresponds to A1G, P corresponds to T1U, D corresponds to T2G and EG. Questions from this, just symmetrical notations have been asked once. Okay. Now, when you consider a complex, you can have both sigma bonds as well as pi bonds, right? We can have both sigma as well as pi bonds. we need to learn the MO diagram of both of these. When you have sigma and when you have pi bonds, you have to learn. Let's say you have sigma bonds. The orbitals that are associated with sigma bonds are S, Px, Py, Pz, and very important, dx square, y square, and dz square. These are the orbitals that are associated with sigma bonds in octahedral geometry. Now, if they ask in terms of symmetry, what are the symmetrical notations? For S, it is A1G. For P, now you know it is T1U. And dx square, y square, dz square corresponds to the EG orbital. So these three symmetries correspond to the sigma bond formation in MO theory of octahedral complexes. While pi bonds are formed by dxy, dxz, and dyz, and these are notated by T2g. So very important, if they ask about the type of d orbitals that are associated with sigma bonds, it is EG. And the types of orbitals that are associated with pi bonds, it is T2g. Okay, so the set is clear. Now, the molecular orbital diagram that we are going to draw is between a metal and the ligand, correct? So on one side, you will have the metal, and on the other hand, you will have the ligand. So we have orbitals, we've mixed them, and based on which we'll have a molecular orbital diagram. Now, without filling the electrons, let's say you don't have any electrons. So any metal, if you take, let's say you take a 3D metal. So what are the possible orbitals that you can have? You can have a 3D orbital, correct? Then you can have a 4s orbital, and then you will have 4p. This is the order of energy. Very important when you do not have any electrons filled. That is the point. I repeat again and again, going back to the general inorganic chemistry concepts, if you do not have any electrons filled, the increasing order of the energy will follow the increasing order of n value. That's all. That's all. Increasing order of n value. But if you have electrons filled in it, then 4s will be least, then comes 3d, and then comes 4p. This is how you fill the electrons. We already know that. Okay, so this is the order without the electrons in it. Let it be there. Now I have just taken a 3D metal. It could be a 4D metal. It could be a 5D metal. Or for simplicity, let me write it like this. N minus 1D, Ns, and Np. These corresponds to the orbitals forming the sigma bond in a metal. All right, you know the symmetries as well, correct? What are the d orbitals? D orbitals are represented by T2g plus Eg, correct? S is represented by A1g and P is represented by T1u. This is how it is represented. Now I want to represent the ligand, any ligand that you take. Okay, let it be any ligand. For example, let's say you took chloride. Chloride is 18. Okay, it ends in 3s2, 3p6. It can have vacant 3d as well. Correct? So here also you have s, you have p, and you have d orbitals that can mix with the orbitals of the metal. Now pay attention to the position of the orbitals of the ligand. Okay, the ligand will have s, ns, np, nd. See, corresponding to this, 3s, 3p, 3d. Whatever ligand you take, this would be the order. So ns, np, nd. What is the symmetry of S? You know it is A1G. Of P, it is going to be T1U. And of D, it is going to be T2G plus EG in the case of MO diagrams corresponding to octahedral geometry. Very important. Octahedral geometry. Now, why have I positioned ligands over here and the metals over here? See, I drew the positions of the metal orbitals slightly higher than the positions of the ligand orbitals. Why is that so? That is because it is based on the electronegativity. Okay. The electronegativity of the ligand is always greater than the electronegativity of the metal. So when the electronegativity increases, correspondingly, the energy of the ligands would be less than that of the energy of the metal. This is one concept that you will be seeing now, as well as again also in charge transfer concepts also. Very important. As the electronegativity of whatever species that you consider increases, the position of the energy decreases. Okay, so chloride being more electronegative than any metal that you take. Whatever metal that you take, chloride is going to be electronegative. So its position is comparatively lower than that of the metal. Now we are going to mix them. Mixing is very easy. You have to mix them according to the symmetry. Those with symmetrical, or the combinations will occur with orbitals with same symmetry. That's all. If you want to note it down, you can note it down. Combination occurs with orbitals with same symmetry. Same symmetry. Which means A1G will mix with A1G. T2G will mix with T2G, like that. That's all. Okay, so let's start. We have to mix them. Now we know that any molecular orbital diagram you might have learned in your early classes as well. It has got both bonding as well as anti-bonding structures. Bonding and anti-bonding structures it has got. Okay, so to draw the structures, first of all, I have to mix. So there would be orbitals that would come below, there would be orbitals that go above. Orbitals that come below and orbitals that go above. So the orbitals that come below will have nature. Let's say I have an orbital over here. Let's say I have an orbital over here, somewhere over here. Understand that this orbital, it is nearer to the ligand than the metal. Correct? This orbital which I have over here is closer to the ligand than the metal. So the characteristics of the orbital that we have got over here will be close to that of the ligand. I'll make you note those points. Just understand that if I have any orbital over here, the characteristics will be closer to that of the ligand because it is far away from the metal. So the order in which it will mixes, understand. See the ligand's order. First comes A1G, right? So let me draw the lines. A1G will mix with A1G. This is my first orbital. And as the energies of the orbitals are lower than the corresponding energy of the metal and the ligand, it is called bonding orbital. It is named as A1G. Next, who is there near to the ligand? T1U. So this guy from the metal will mix with the T1U of the ligand. And you get the second orbital. Next, we are talking about the sigma bonding cases. Okay, whatever we are learning is with respect to the sigma bonding. So in sigma bonding, by now we know that Eg is what is involved. Correct? Eg is involved. So among the d orbitals of the ligand, only Eg will participate. Only Eg of the ligand will participate with the Eg of the metal as well. This is the diagram. Can you see? So the mixing is like this. It follows the order of the ligand because the orbitals over here are closer to that of the ligand. So it's A1G, T1U, Eg. These are the bonding orbitals. Bonding orbitals. As the bonding orbitals are more closer to that of the ligand orbitals, they have higher ligand character. Have higher Ligand character. Okay, now it's the time for antibonding. Antibonding means whose energies will be higher than the corresponding two. Corresponding two means corresponding metal and the ligand. So if you have any orbital whose energy is higher, their characteristics will be more closer to the metal than the ligand. Correct? If I have any orbital over here, its position is nearer to the metal than the ligand. So the order will be that of the metal. What is the order? See who's the lowest? Eg. So now you have Eg star over here. So this is Eg star. Next is Ag, right? Then you have A1G star. A1G star. Please draw the lines correctly. And then you have T1U star. T1U star. Very easy if you pay attention to the classes. T1U star. That's it. Okay. So the antibonding orbitals follow the order Eg star, A1G star, T1U star as that of the metal. So these are the antibonding orbitals. Antibonding orbitals who are nearer to the metal. If they're nearer to the metal, they have antibonding orbitals have higher character of metal. Right? These are closer to the ligand and hence they have higher character as that of the ligand. So see the order A1G at the top, sorry, bottom. T1U, next comes T1U, and then EG, next comes EG. So this is how you draw the sigma bonding molecular orbital diagram. One important point. If you consider the metal's T2G is vacant. Not vacant, it's not used up in the molecular orbital diagram. So that has to be written as it is because it's not used. This is the T2G of the metal, which is not used in the mixing, and this is non-bonding. So can you see the three different types? You have bonding orbitals, you have anti-bonding orbitals, and you have non-bonding orbitals. Now in CFT, we learned that the crystal field splitting energy is the energy gap between T2G and EG. Am I right? Now can you see this? T2G EG gap over here is what is written as crystal field splitting energy delta O. So according to the adjusted CFT or LFT, it is the gap between the non-bonding T2G with the anti-bonding EG that is represented as crystal field splitting energy delta O. Okay, so this is the MO diagram. If you read it for a couple of 2 to 3 times, this is going to be very easy. Don't worry. So it's just that we have taken a metal. Metal has got d, s, and p orbitals. Ligand has also got sp,d orbitals. So first they will mix in the order of the ligand. So the order of the ligand is A1G, T1U, and EG. Now anti-bonding orbitals have got characters of that of the metal. So it will follow the order of EG star, A1G star, and T1U star. That's it. The T2G of the metal does not participate in sigma bond and hence it will remain as non-bonding. As it will remain non-bonding, the energy gap between this T2G non-bonding and anti-bonding EG star is what is known as crystal field splitting energy according to the adjusted CFT. That's all. Okay. So now we have learned only about sigma bonding. We need to learn about pi bonding as well. So let's learn. Write the next heading, pi bonding. So now you know how to write the splitting in accordance with the sigma bonding. Now write the next heading, pi bonding. Pi bonding. So in pi bonding, what you have to understand is, which I had also spoken in the electrochemical, sorry, not electrochemical, spectrochemical series, that the ligands according to CFT are of two types. Okay. One type of ligand is called pi donor ligand. Pi donor, or in question papers, you can also see this word called pi basicity. Both of them are the same. Or the ligands can be called as pi acceptor ligands. In question papers, you might see this word pi acidity. Both of these are the same. Okay. So ligands can be classified as pi donors or pi acceptors. Any ligand that you take, we have learned a very big spectrochemical series. Okay. Iodide, bromide, sulfide, chloride, fluoride, urea, whatever ligand that you take, every ligand, whatever ligand that you take, is a sigma donor first. Very important. Whatever ligand that you take, that's true, right? Any ligand that you take will have a lone pair of electrons which can be donated to the metal. So that is the definition of a ligand. That is a function of the ligand. So any ligand that you will take will be a sigma donor first. Okay, so that is though by default a property of a ligand. If it has to be a pi donor, they must have at least two lone pair of electrons. At least two lone pair of electrons. Then only they can be called as a pi donor. Okay, for example, let's say you take chloride. So chlorine is actually 7. Chloride means it will take one more electron. So this is chloride. So the first pair of electrons will be donated to the metal to form the sigma bond always. If there is an extra lone pair, that will be given to form the pi bond. So it needs at least two pairs. I hope you understand. So whatever ligand that you take must have at least two lone pair. Let it be chloride, bromide, sulfide, iodide. You got the point, right? So all of these are pi donors. Pi donors. Now, if you want to see pi donors, it would be at the left end of the series. Left end. Those are the weak ligands. Generally, those are the weak ligands. Okay. So if you need a pi donor, your metal's oxidation state should be high. Metal should be in high oxidation state. Am I right? Why? Because it is receiving a lot of electrons. So the electron density at the metal should be low. Okay, so the metal's oxidation state must be at least equal to or greater than +2. More than +2. Then only pi donors will come and attach because it receives a lot of electron density. So that's about pi donors. Now, next one is pi acceptors. Now we will see that why pi donors are weak. We will see it in the diagram, or if we want, let's do it now itself. So T2G orbitals, which we said. So from the previous diagram, we know that Eg goes for sigma bond formation, and you have T2G which goes and forms the pi bond. Correct? Now, T2G in the earlier case over here, when we drew the MO diagram for sigma bond, it was non-bonding. Okay. Now, this non-bonding T2G, this T2G of the metal will combine. Now, we have, see the diagram over here. You have T2G and above which you have Eg star. Okay. So, I'm just taking this part of the molecular orbital diagram for the pi bond formation, this part. I repeat, I'm taking this part. Okay. So you have T2G and you have Eg star over here. The gap between these two is actually the crystal field splitting energy is what we told. Now we are going to, so this is the case of sigma bond formation. Correct. Now we are going to talk about the pi bond formation. So when pi bond, the metal T2G will mix with the ligand T2G. the position of the ligand orbital would be lower because the electronegativity of the ligand is higher. Okay, so they'll mix. So once they mix, you get T2G over here, forming the pi bond, correct? And you have got T2G star over here. Very easy, only this much. So the T2G orbitals of the metal combines with the T2G orbitals of the ligand to form the pi bonds. These are responsible for the pi bonds. So this is the case when you have a pi donor. Understand? This is the position when you have a pi donor. Pi donor ligand, very important. Now, if you can see, this is T2G. If I draw the position of the EG star, can you see that T2G EG gap has now reduced? Let me write it as delta O prime. So we can see that when you have a pi donor in the system, the splitting between T2G and EG represented as delta O prime now is less than delta O. Or in other words, this is again a supporting evidence to what we learned in CFT. Pi donors are weak. It is because pi donors are weak, the splitting is small. Earlier, when you did not have any pi donors, when you have only sigma bonding ligands, you can see that the splitting between T2G and EG is huge. But the moment you have some sort of weak ligand or a pi donor ligand coming, the spacing decreases. That is because now the spacing is between T2G anti-orbital and EG anti-orbital. And hence, pi donors are weak. This is an evidence which was put forth by LF. Now, we also know that there are another type of ligand which is pi acceptors. What about pi acceptors? We said there are two types. One is pi donors and the other one is pi acceptor ligands. Pi acceptor. So pi acceptor, for example, it will have one lone pair, of course. Will have one lone pair because any ligand will form a sigma bond first. That is for sure. For which it needs one lone pair. Okay. Along with that, it must contain pi star, or I'll write contain vacant pi star. Contain vacant pi star or vacant d orbitals. Okay? So that it can accept the electron. Let me tell you an example. Let's say you have a metal. Okay? And you have a ligand like carbonyl. CO, carbonyl. This is how the ligand is. So this one pair of electrons from the ligand will be donated to the metal to form the sigma bond. Now what will happen? The filled orbitals of the metal, will back donate the electron density to the empty pi star orbitals of the ligand. I repeat, the first process is formation of a sigma bond. The second process is from the metal, the electron density is put into the pi star orbitals of the ligand. So if there are pi bonds, there would be pi star bonds as well, right? So this back donation happens if the metal is in low oxidation state because it has to give electrons, correct? So this is preferred by systems where the metals are at low oxidation states. What are the examples? Carbonyl, nitrosyl, Cn minus. These are all examples where these are called very strong ligands, or you call it pi accepting ligands. Now we need to learn how do we see them in a MO diagram. Okay, so already we know that if you have a sigma system, you have T2G over here and you have EG star over here. This is something that we know. Correct? This is the position of ML in sigma bonded or octahedral complex. Now to this T2G, you're adding a pi bond which is formed by a pi acceptor ligand. Understand, pi acceptor ligand. So if you have a ligand, pi bonds would be here. Listen to this carefully. Pi bonds would be here, but we are not considered with the pi bonds. We are considered with the, not considered. We are concerned with the pi star. Pi star orbitals of the ligand. Can you understand the difference? See, in the earlier diagrams also, we learned that bonding orbitals would come at the bottom and anti-bonding would come at the top. Correct? The same principle for ligands as well. If you take any ligand, pi bonds would come at the bottom, which we do not need over here because electrons are received to the pi star orbitals and that comes at the top. So here, the position of the metal T2G will be lower than the anti-bonding pi star orbitals of the ligand, which has also got the same symmetry, T2G itself. Now, if you mix it, what will happen? This will mix to form T2G and it will mix to form T2G star. The diagram is simple, but look at the concept. Now EG star comes over here, no change in the position. Can you see that the gap has increased? I'll write it as delta O double dash. So this was delta O earlier when you had just sigma bonds. Now the moment there is a pi acceptor ligand. Pi acceptor ligand, wherein the electrons enters to the pi star orbitals. So the moment that has come, the splitting delta O double prime has now increased than the normal splitting, meaning pi acceptor ligands are strong. Pi acceptor ligands are strong. Okay, so I'm stopping it here. I have to take the molecular orbital diagram of tetrahedral complexes as well, but then I'll pause because it is something new and a bit advanced. So please revise this before listening to the next video. So I'll stop it over here. I'll do a quick revision before the next video as well. Yeah, so see you in the next.